Hello, beautiful people, and welcome. In this video, we're going to be talking about how to graph polynomial functions. Now, I'm going to be completely honest. This is one of my favorite units. I absolutely love it. I think it's an amazing way to graph polynomial functions. I am assuming that you have watched the leading coefficient video. You are expected to know the end behaviors of these. And if I make a mistake, let me know where the mistake occurs. I definitely want to learn from my mistakes, but I'm excited. Let's go ahead and get started. So graphing polynomial functions. I'm going to start you off with some steps. We're going to be working with factored form. So what that means is we're not expanding them. We are actually given the factored form. And you're going to see something like this. So let's do an example and steps at the same time, just so you know what I'm referring to. So let's do example 1, jumping right into graphing these. So this is a polynomial, that's a 3. This is a polynomial function. Let's make it into a function. Sometimes you'll see this, sometimes you won't, but this is a polynomial function in factored form. It just means there's lots of terms in here. Now, factored form is not expanded, so what you have is you have these bubbles. This is what I call the bubble. So a bubble, let's actually do a thinking bubble for the bubble. I'm going to be referring to bubbles. And bubbles are just grouping for parentheses. So these are the grouping for parentheses. So I have one bubble here, I have one bubble here, I have one bubble here. So each bubble will have an exponent. Okay, so each bubble will have an exponent. We have bubbles. Here's another bubble. Each bubble will have an exponent. So when they ask you what is the total degree of the function, when they ask you what the total degree of the function, what they are saying is take all exponents. And I'm going to write seen and not seen. And I'll show you what I mean by that in a second. And add them together. Okay, so what does it mean seen and not seen? So if I'm calling something seen, that's a bubble having the exponent of 3. I can see that exponent clearly. It's 3. Now, a bubble that is unseen is having something like x plus 3 or simply x. There is no exponent that is seen there. However, there is a major exponent there, and that exponent is 1. Okay, so what is the total degree of the function? In factored form, you're going to take all the exponents, seen and not seen, and add them together. So anything in a bubble, it will have an exponent. X is in a bubble, but mathematicians are what? We are lazy. So X is in a bubble. Whenever you see X, it is in a bubble. We just are too lazy to write it because it is singular. Okay, so that is how you find the total degree of the function. Now, leading coefficient. What is the leading coefficient? What is the leading coefficient? So all you have to do for the leading coefficient in factored form, love it, is just look at the first number that you see. This is the first number that you see. Oh, that was bad choice of color, choosing yellow. Let's go ahead and choose a different color. Leading coefficient, LC, is the number out in front. So what is the leading coefficient? The number in front. And we can call this A if you would like to. Okay, step number, well, not technically step, but questions. We'll get to steps later. Question number 3. What is the end behavior? So end behavior is how the graph, let me change markers, how your function behaves how the function behaves. Why can I not spell that right now? How the function behaves? Oh, that's wrong. It's okay. I'm gonna know that's a spelling error. It's okay. So how the function behaves as x approaches infinity and as x approaches negative infinity. So as x approaches infinity and y approaches infinity, something happens. We need to figure out what that end behavior is. All right, question number 4. You know what? I wasn't half bad. I'm looking this word up right now. That's why there was a moment of silence there. But behaves, I was right. There was no I, but behaves. That just looks weird to me. It's okay. So now it's not a spelling error. I fixed it. That looks weird. It's okay. All right, question number 4. We want to talk about zeros. And actually, let me rewrite question number 4 on a different page because I do need a little bit of space to talk about your zeros. So we're asking to identify the zeros. What are the zeros? Those are your x-intercepts. So those are on the x-axis. And we're going to identify the x-intercepts, where they cross. So x-intercepts is super duper important. Now, how to find zeros? I'm going to show you 2 different ways. So the first one we can do, let's say we have a bubble. Let's say we have 2 bubbles. And to find a zero, you're going to take each bubble. You're going to set it equal to 0. And then you're going to solve. So I'm going to add 3 to both sides. Add 1 to both sides. So I have x is equal to 1, and I have x is equal to 3. So for this bubble right here, let me rewrite that, you guys. I didn't realize you didn't see. Okay, so for this bubble right here, for x minus 3 bubble, you have a 0 at positive 3. And then at x minus 1, you have a 0 at positive 1. So this is how I like to do it. I actually don't prefer this. I feel like that's too much steps. So if we have our bubbles, I'm looking at each bubble individually, and I'm asking myself, what does x have to be in order for the bubble to be 0? And again, I'm looking at each bubble individually. So this question is being asked many times. Let me change the color so you know that I'm asking this question many times. And let's write out that question. What does x have to be for the bubble to be 0? Ultimately, we're doing this. We're doing this, but we're doing this in our head. So if I have a -3 here, what does x have to be in order for this bubble? Don't worry about the squared, just the bubble to be 0. Well, if I have 3 minus 3, so that means x is 3, and that is my 0. Again, here, what does x have to be in order for this bubble to be 0? I have x minus 1, so if I have 1 minus 1, that means my 1 is my 0. And again, what are zeros? Zeros are x-intercepts. That means I'm going to have an intercept. I'm going to have a point or a crossing or a touch, something at x is 3. So we're going to have something there. And I'm going to have something at x equals 1. We don't know what that something is yet, but we're going to do that. Step number 5 or question number 5 is how do they cross? How does the function behave? Well, now I can spell behave. It still looks weird though. Behave at each 0. And again, a 0 is an x-intercept. So how does it behave at each 0? This is where we need to go back and talk about functions in general. So we have different functions. Functions can be in the form of different things. If you have an exponent of 1, for example, if you just have x, or you have x, I don't know, plus 5, your exponent is 1. We already discussed that in a previous, it's the unseen exponent. So we have an exponent of 1. If you have an exponent of 1, that means that bubble is linear. If you have a linear bubble, you will have a line going through that x-intercept. And again, x-intercept is just your 0. So if you have an exponent of 1, you have it crossing. Now, let's say you don't have an exponent of 1. Let's say you have an exponent of 2. Or 4, or 6, or 8, or etc. It is an even number in your exponent. For example, x minus 5 squared, x to the 4th power, I don't know, x minus 7 to the 8th power. Doesn't matter, the exponent is even. Whenever you have an even exponent, it's going to look, when you graph in the even, like x to the 4th power, it really, here's the thinking bubble, it comes from the parent function of a parabola. So we have a even function, or even, let's not call it function, let's say even bubble. Since I'm using bubble here, I want to stay consistent. We have an even bubble. So what you're going to have is you're going to have a parabola looking. We're going to kiss the x-axis at the 0, at the intercept, but we are not going to cross. We cannot cross. Okay, if it's even exponent, we cannot cross. So we have a linear, we have an even, no crossing. We're going to kiss it. All of this will start making sense when we do an example. And then we have the exponent of 3, 5, 7, etc., odd. So if we have an odd one, let's say x to the third power, x minus 5 to the, I don't know, ninth power, x plus 2 to the fifth power, something like that. But the exponent is odd. This is what we're going to call a Mr. John Travolta. So it kind of looks like a cubic function. So if it's something's cubed, we know it's a cubic function. And then the 9 and the 5, all odd functions will resemble some sort of Mr. John Travolta, some sort of curve that looks like a cubic function. Go ahead and practice if you want to go on to Desmos or GeoGebra and type in x to the third, x to the fifth, x to the seventh power. You're going to see that all of them they're going to look similar. Obviously, they're not going to be the same, but they are going to be similar with that shape. So let's go ahead and do that shape just to give you an idea. And this is all assuming that we'll talk about that later. Okay, so if it is odd, this is the shape. Again, this is not exactly how it's going to look like, but this is the shape right here. So it is going to be an odd bubble. And with an odd bubble, you're going to have what we're going to call a John Travolta. That means you're going to have a curve through, you know what, as the video keeps going, I'm just getting better and better at spelling. We're going to have a curve through the x-intercept. And we're going to treat the x-intercept like the vertex. So that's where the curve is going to happen. Now, the curve can be this way. The curve can be that way. Just depends on your end behavior and what your zeros, what you have. Same thing here. This can be positive. This can also be negative. It can be shifted this way, that way. It just depends on what you have for your zeros and your end behavior. So it can be this way or this way, increasing or decreasing. So we are going to have a curve through the x-intercept. You're going to have a curve through the vertex. Again, it's going to be the 0. And you're going to treat that 0 like it's the vertex of a cubic function or the fifth or the ninth, all of that. Okay, now that you have all of that, step number 6, I barely have room for it, but step number 6 is combining all of that. Since you have a function, okay, so how do you combine for the final graph? So when you combine for the final graph, you need to make sure that you remain a function. So for example, if you have something that looks like this, and you have your zeros, let's say you have 3 zeros, 1, 2, 3, your end behavior is going up and your end behavior is going down, so you have a decreasing function, and you have a parabola here, so you're going to kiss it. You have a John Travolta here. So you can't cross the x-axis unless you have an interceptor, unless you have a 0. So in case this way, you have to make sure that you don't do something that looks like this. Let me try to make it bigger. Like that. Do you see how this no longer is a function? Let's do the vertical line test. Vertical line test says if you have a vertical line, it can only hit once. Notice I have a 1 point here, I have 2, I even have 3 if I drew it this way. So make sure that the way you're drawing your John Travolta's, the way you're drawing your parabolas, they do not overlap with the other ones. So you have a curve, and then let's say you have a line, oh, let's say you have another parabola, and you connect it down. But it has to remain a function. So if I was to draw a line all throughout here, it only can hit once. It's super important that you don't make this hiccup. And how do you combine for the final answer? You need to stay a function, and you need to connect. Only available are the zeros, or your x-intercepts. So you cannot cross anywhere else. If I need to get to this 0 or I need to connect somehow, I cannot cross the x-axis without a 0. I cannot cross the x-axis without an x-intercept. Big no-no. Okay, the only zeros we have, the only x-intercepts that we have are the ones that we identified in the beginning. We cannot create more just because it fits our graph. Okay, we have to only work with what's given. So how do you combine for the final graph? You need to stay a function. You only available are the zeros or the x-intercepts, same thing. And you need to connect to your end behaviors. End behaviors are these. So we have a decreasing graph going from left to right. We're going downhill. On our left-hand side, we are going up for our end behavior. On our right-hand side, we're going down. So as x goes to infinity, y goes to negative infinity, y goes to infinity. As x goes to positive infinity, y goes to negative infinity. All right, beautiful people, I'm going to wrap up this video. We didn't actually do an example here. That's okay. Go ahead and continue to the next video. I hope this helps. This is kind of the steps that we're going to do. And by kind of, these are the steps. I did something different, apparently, with doing it as a question and answer type of steps. But make sure you have all of this ready and handy. So when we start the next video, we can jump in right into an example. Thank you so much for watching our video, and I will see you next time. Bye.